Hello everyone! In this video we will continue to examine topic 5.4, the magnetic effects of electric currents, and in particular we will discuss the magnetic field of a current carrying wire. Alright, so at this point we are equipped to delve down into sort of the fundamental source of magnetism. And it has a sort of surprising answer right at the end of this. As it turns out, currents also produce magnetic fields. And actually, as it turns out, currents are the only things which produce magnetic fields. So what do I mean by a current? Eventually I will mean simply moving charges. And the big idea is that moving charges produce magnetic fields in addition to electric fields. When you have a moving charge, you get a magnetic field. Straight up, full stop, that's the source. And so when we have these bar magnets, we're going to have to sort of fundamentally explain it in terms of this. So, now why aren't we familiar with this, right? We have a lot of electric current in our lives in different places. Why is this not familiar? Well, fundamentally, the answer to that is for a regular current carrying wire, you would need a gigantic honking current in order to detect any sort of magnetic field. So our most fundamental understanding of this magnetic field takes a lot to see or experiment with. You can do it, but if you're just having a simple wire with current in it, you need a huge current to produce a strong enough magnetic field to detect. And so what does this current actually look like? All right, well, imagine you have a section of wire, okay, straight wire, and the current is going in this direction. So charge is flowing in that direction. The magnetic field looks like shown, and it has a couple of different features to be aware of. The magnetic field is fundamentally in the structure of concentric circles or closed loops. Okay, so the magnetic field around a current carrying wire is in, or that will be produced, is in this closed loop structure. If you took a compass and you put it all the way around the wire, you would see that the vector direction at any particular point is going to wrap around the wire. They are concentric circles centered on the moving charge, and they are fully closed. The magnitude of the field decreases with distance, which we'll talk about in a minute, which makes general intuitive sense, and is symmetric along the entire length of the wire. So actually, it's not even just that they're closed loops or circles. Really, if you visualize it, they're sort of cylinders of magnetic field. Okay, so they wrap all the way around the wire for the sort of duration of the current, and they increase with the current. Now, you can actually find the magnitude of the B field for a current carrying wire. There are very few times when I think the IB doesn't give you an equation. They probably should, but this is actually one of them. And I'm going to introduce an equation that I'm not going to expect you to use, but might make things a little clearer. So as it turns out, you can find the magnitude of that magnetic field using this equation, which can be derived in using some more advanced mathematical techniques with a little bit more of information about how magnetic field works a little later on. But the general structure is as follows. Notice that the magnitude of the magnetic field is proportional to the current. So if you increase the current, you increase the magnetic field, and it's directly proportional to the current. And it's inversely proportional to the distance away from the wire. Notice, not the distance squared, just the distance. So as you go further away, the magnitude of the magnetic field drops, but it's only a 1 over r formula and not a 1 over r squared formula. 2 pi should be familiar to everyone, but this constant, this mu0, is known as the permeability of free space. Notice this is very close to epsilon naught, the permittivity of free space, and you can think of mu0 as being like epsilon naught, but for magnetism. It basically says, here's how sensitive a vacuum is to magnetic field. So if I have a certain amount of current, how much field do I get? That's the proportionality constant. and it has the same relationship to magnetic field as epsilon naught, or the permittivity of free space, does for magnetism. Again, you won't need to know this formula for the IB, but it can actually make some things clearer, and we're going to use it in a couple of derivations later on. So this is the magnitude of the magnetic field for our current carrying wire. And finally, the most important thing to keep track of for the magnetic field due to current carrying wire is what direction the field is circling in. Is it clockwise or counterclockwise? And the way to figure it out is to apply what's known as the right-hand rule. Side note, there are several different right-hand rules that exist. I'm going to teach you a single one, and I'm going to be super consistent about it. So it doesn't matter the textbook, doesn't matter what else you're using. I'm going to be super consistent about the right-hand rules I teach you to try not to confuse you. There are other versions, unfortunately. But here's the one that I'm going to give for magnetic field. In this, you take your right hand and you point your thumb in the direction of the current. Okay, so your thumb goes in the direction of the current, and then what'll happen is if your thumb is in the direction of the current, then the fingers of your right hand will curl in the field direction. So thumb in the direction of the current, then your fingers on your right hand will curl in this direction if you sort of semi-close your fist, if that makes sense. So that's how you find the magnetic field direction. This is, for those of you with the math, a little bit of a backwards way of doing what is ultimately sort of a cross product. But we'll see that a little bit later.